My name is Bojan Nikolic, I've been invited here to tell you about a radio astronomy project, in fact, called the Square Kilometre Array. We have a little bit of a grand title for the talk, but it's mostly about astronomy. So I just want to say thank you to the organizers for inviting me. I think I have a personal interest in big data, and also, as you'll see shortly, we have a very big professional interest in big data, because big data is what's going to make this radio astronomy project work. So I'm here to learn as well as tell you a little bit about what we've been doing. So first, I'd just like to make some excuses for the grand title of this talk. So I'll just give away the talk really and say the reason I have this title is because I'm going to redefine what big data means in this talk. And that's why I get away with being able to say it's the largest big data project in the universe. Because I think what most of the people in this room do to say it's big data, it undersells it a little bit, because most of the big data today is about big information. You have a very high information density in your data, and it's about summarizing that information. So the radio astronomy project I'm going to talk about is really about big data, and most of that data is noise. And my job in my current position is to understand how to extract the relatively small percentage of information from that large data volumes. Right, so as I mentioned, this talk is about the Square Kilometre Array. So what is the Square Kilometre Array? What is this radio telescope? So this telescope will be one of the cornerstone observatories supporting astronomy for the next 50 years. Right? So a lot of astronomy is done today with relatively small experiments, which are organized by universities and groups in universities. But as the demands for resources increase, more and more we're getting to an area where we are consolidating into a few very large international facilities which are supporting an ever increasing fraction of astronomy being done. So it is the astronomical community around the world foresees a handful of major observatories supporting the majority of astronomy in the next few decades. So those facilities are foreseen to be ALMA, which is a high-frequency radio telescope in Chile, the European Extremely Large Telescope, which is also going to be in Chile, the JWST, the James Webb Space Telescope, which is going to be the replacement for Hubble, and that's going to be at the L2 point in space, obviously, and the Square Kilometre Array. So the Square Kilometre Array really is a partner to these other facilities, and together they will be supporting the astronomy programs in the in the long-term future, really. So these type of projects are all large international projects. They all have budgets in close to or above billions of dollars or euros or pounds. That's more or less the same now. They take a long time to build. The space projects in particular have a very, very long lead time, and they have very large budgets. But they're all big international collaborative construction projects, and then they're operated as a collaboration between many nations. And that's true for the Square Kilometre Array as well. So what is going to be, what's the defining feature of the Square Kilometre Array? This image tries to convey this, and I think the main thing I'm going to say is that this is astronomy at mass manufacturing scale. That's the vision of the SKA. Right? That we really start employing mass manufacturing to capture as many of those photons coming to us from space, and then we process them using computing technology. Right? So we want to. That is the vision of the SKA. So this is an image. This is obviously an artist impression. Okay, so the SKA is still in the design phase, and we're going to be entering the construction phase in the next 2 years. We have most of the money secured. The UK government is supporting the Square Kilometre Array in a very significant way, which we're thankful for. So this is an image or an artist's impression of what the Square Kilometre Array will look like in Western Australia. And if I just add a zoom in, so you can actually see what it looks like. So this is the low frequency part of the Square Kilometre Array. And as you can see, they sort of look, the receptors of the Square Kilometre Array, so the antennas which receive the photons and do the observations, they look a little bit like misshapen shopping trolleys. And they have a budget of about 100 euros each. And then you have a sea of those, right? And so what you see in this main image is just a sea of these antennas all over the desert. And in total, there will be 100,000 of these antennas in Western Australia in phase 1 of the SKA. So that's the low frequency instrument. At the higher frequencies, this is what it's going to look like. So the higher frequencies are going to be sited in southern Africa, mostly in South Africa, but also in neighboring countries. So they're at the slightly higher frequencies. We have a technology which looks a little bit like giant satellite dishes, but again, mass manufactured, and we have a sea of those. So in the first stage, there's going to be 256 of these 15-meter antennas, and then increasing to maybe as much as 1,000 in the second phase. So those are the actual telescopes forming the SKA observatory, the actual hardware, the tin on the ground, so to speak. So the observatory itself, though, is much more than just these receptors of photons. So the receptors is what I've shown you in the images, but what you don't see in the images is the digital signal processing, and in particular, the data processing, so the general purpose computing, which is a key part of the SKA. So during this talk, I'll explain why computing plays such an important role in the SKA, why actually our requirements are quite similar to a lot of the big data projects. They're also different in some key aspects, and I'll explain a little bit about how we're going about designing and soon to be implementing the system. So, but first I want to tell you about the science and what it is that the Square Kilometre Array intends to observe. And I think, so in an observatory, any observatory like this, which has a large investment up front, of course, we've analyzed the possibilities of what it's going to observe, and we've assembled a set of key science cases, which are going to be, we think, very interesting. So we can call these the known unknowns. We don't really know that we will be able to observe this, but we think we will, and we think it's going to be exciting. So there's a whole set of those. There's two key science drivers for the SKA. The first of those are gravitational waves. So just in the last 6 months or so, we had a very exciting, very first detection of a gravitational wave. This detection was done using a laser interferometer on Earth, which is based in the US. And what the plot on the left shows you is the actual measurement recorded by two of these interferometers. And on the right, you see a reconstructed signal, so you see an oscillating signal which gets faster and with a greater amplitude as time progresses. And what we are seeing there is a merger of two black holes. So this is a great, exciting discovery. So the plot on the bottom here shows the velocity and the separation of these black holes, and you can see the velocities we are measuring are around half the speed of light, and the separation is right down to 1 Schwarzschild radius, so right into the merge of these black holes. So this has been a great, amazing discovery, and it's also shown and proven that gravitational waves exist, which is great for the SKA. Because now we know this is a new window on the universe. Then we can we know that the SKA, the Square Kilometre Array, will play a big role in investigating the gravitational waves in the universe. So this graph shows where the niche of the Square Kilometre Array is going to be. So the plot I showed you is in the regime at the very right side of this plot. So we are right in this where the purple colors are, and this was a prediction actually. So this is before the first measurement was made, and indeed, the first detection was made exactly where those predictions forecasted would be. So what the SKA, the measurement was done at around 100 hertz. So those black holes orbit each other around 100 times a second. So what the SKA is going to do is measure the same type of physical effects of the gravitational waves, but at 10 orders of magnitude a lower frequency. So the SKA is going to look at much longer wavelength gravitational waves. So the SKA is aiming. So this is the regime where SKA is trying to operate, and we'll be measuring gravitational waves. So measuring waves with periods of years. So 10 to the minus 8 hertz is about a few years, and characteristic strain. So the characteristic change that the SKA is going to measure is 10 to the minus 18 relative change. And how is this? How is it going to work? Well, it's going to work by using pulsars. So the Square Kilometre Array will first survey the sky to find thousands of fast pulsars, and pulsars are natural, extremely good natural clocks. And by observing many, so this is an image of our galaxy, and the yellow dots show a simulation of how many and where we think we're going to find these pulsars. And by simultaneously, or nearly simultaneously, measuring the timing signal from many of these natural clocks in different directions of the sky for a period of a year or several years, the Square Kilometre Array will be able to detect these tiny changes in really the structure of space, and therefore see the gravitational waves passing through our galaxy. So this is going to tell us, so we're going to see this, we think, we forecast that we're going to see this new window on the cosmology and the universe. And that's one of the key science goals. The second key science goal is something called the epoch of reionization. And the epoch of reionization is a measurement of the pathway history of the universe where we have at the moment no way of seeing or constraining what it looked like. And this is the epoch which is labeled here in this diagram, the Dark Ages. So this is the epoch where there was hardly any galaxies, and there's only the first stars and the first black holes started to turn on. And most of the universe was neutral and pretty opaque to most types of radiation. So we have no hope of seeing those stars and those initial quasars and black holes because they're just too far away and they're going to be too faint. Too much of their radiation is going to be absorbed by the surrounding medium, by the neutral medium around them. But the epoch of reionization experiment will actually look at the imprint of these first stars onto the neutral gas around them. And by measuring one of the transition lines of hydrogen, we're actually going to see the holes in that neutral gas forming at very large scales and actually be able to see the statistics, if not the individual first stars and galaxies. So those are the two main drivers. So they're quite exciting. Probably the most exciting thing are the unknown unknowns, so the things we haven't thought of, which we're just going to see by accident by building a new observatory which is 100 times more powerful than anything we have today. So it's very difficult to illustrate the unknown unknowns, but these two slides are going to try and do that. And what this shows is a comparison of what the Hubble telescope sees in a deep integration of the sky, and more or less the same region of the sky observed with the best current radio telescope called the Very Large Array. And what you can see that the current radio telescopes see only a very small fraction of the sources we see with our current best space optical telescopes. Well, the SKA, we think, is going to transform that. And we're going to see just as many, if not more, sources in the radio than we do in the optical, and we're going to get more information out of them. So yeah, we have good cause to think we're going to find something unexpected. And that's probably the most exciting thing about the Square Kilometre Array. So why am I here? And why am I here at the Big Data Conference? Well, computing is a major part of the Square Kilometre Array, and it is a major part by design, because we realized we can make use of the advances in computing and ICT technology to make the Square Kilometre Array possible. And this can be summarized by what we in radio astronomy call the difference between large D, large diameter telescopes, and large N, many but small telescopes. So the image on the left is the Green Bank telescope in West Virginia in the US. So it's probably the largest moving man-made structure in the world. So it's 160 meters from bottom to top. It's 110 meters from side to side. And it's the largest steerable single-dish telescope in the world. And the image on the right are these Square Kilometre Array antennas. So the idea of the Square Kilometre Array is to build cheap antennas, connect them up, and then do the imaging and the adding up of that radiation that we're receiving in computing. So do that all digitally, do it in general purpose computing. Whilst the old single dish telescope effectively does that in an analog way. By having a shaped surface, it actually forms, it adds up the radiation in the right way analogically. So we're moving into pushing all of this hard work into computing. And the reason we do that is that now it is much cheaper to do that. And we can actually, these antennas, so the GBT cost $100 million. This telescope costs $100 million to build. Each one of these antennas costs only $100 to build. So even with 100,000 of the antennas on the right, the actual construction cost is only 10 million. And yet the collecting area that these antennas cover are almost 50 times greater than the big antenna on the left. So this is good. We spend less money on boring bits of steel on the ground, but it does mean that we have to invest proportionally more into computing, where all the hard work now gets done. And this is where big data comes in. And there's a whole chain of computing that we have to do. The bit I'm going to talk about is the most challenging part, which is labeled the SDP here, the Science Data Processor. So this is where we use most energy, we're going to be using most flops, we're going to be using most storage. So if I summarize the system that we're designing in this graph, there's two key numbers that or three key numbers that I want to show you. So we get this telescope, this part of the system will get data at 1 terabyte a second in, right? So 24/7, 1 terabyte a second are going to be coming in. Each observation is going to take about 6 hours. Total amount of data, once some overheads are taken into account, about 100 petabytes per observation. And this computer will have about 100 petaflops of computing power. So these are big numbers, and that's why I'm here, the Big Data Conference. And what the job, and my job is, to take this 1 terabyte a second of data and extract the information from it, and then discard the data. So we can't keep 1 terabyte a second permanently. The volume of that is too high. And we don't need to, because the information content in this data is about, it's quite a lot less than 1%. So this is, I think, one of my main points, and I think this is an area where big data will evolve in soon. Is that it's really going to start? It's going to be more about extracting information from really a noisy data streams, stochastic data streams, because we captured the human-generated information already. And what's going to be, the next deluge of big data, sensor big data, when the information content isn't that great. So this is an illustration of what a radio telescope sees. It's an illustration, it's a simulation. But what you see is that each individual measurement is a very noisy measurement. So there's fringes behind this measurement. because these are interferometers, so they actually see fringes at the end of the day. But so each measurement is very noisy, and the job of the science data processor and the key part of the Square Kilometre Array is to add up those data in a way that we can actually see clearly this real signal behind this noise. And so it's all about averaging in the right way, of course, the information we receive, the data we receive. So that's very different from a diagram like this, which shows, of course, the way data works on the World Wide Web, where there's a huge amount of information in each byte. Right. So those are the major differences. So we're talking about small information content, large natural size data. We're talking about gigabytes chunks of data. Intermediate total operational density of about 1,000 operations per byte. And relatively regularly sampled data. Also, the conventional big data is sort of quite different. I'm accentuating the difference, of course, so you can relate to this best. There is a new field, I guess what we could call big learning, which is the deep neural networks and so on that a lot of companies are making a big investment now in, and that is perhaps in between these two types of big data. Right, so I'll just move on very quickly on how we're doing this. So we actually know quite well through models and analysis what sort of a system we need to build to address this challenge. So it is about 100 petaflops. That's a lot. It's not impossible. We actually need one of the key challenges is the aggregate memory bandwidth. So we've done the analysis, and we think we need about 200 petabytes a second of memory bandwidth in this system, which is a big challenge. And the I/O rates we foresee is about 10 terabytes a second of read bandwidth. So these are large numbers, but I think the good news is we think we know what they are. So what does that mean? So we think we've analyzed what the hardware needs to do, and we're going to build the hardware which we think is going to be pretty well suited for this, obviously from common off-the-shelf components. So we're going to balance the system for this problem. So unfortunately, I think if the hardware is well balanced, it doesn't mean the software is always going to be the bottleneck. So there's fewer people to blame when things go wrong. So I think that again is a different situation from where big data started from in the commercial world, which is you repurpose systems, and you can get away with doing software in a much less efficient manner because you had lots of spare cycles, for example, processor cycles in a conventional big data system. We won't have that. So the implications for us, and I think for some of the other projects, such as big learning and other sensor big data projects in the near future, is memory bandwidth is very important, and you have to start thinking of the architecture of your computer system not as a collection of disk drives, not as a collection of processors, but really you're driven by the collection of your high memory bandwidth stacks, and that is what defines the architecture of your system. So this is an illustration of a GPU using high bandwidth memory, so that the central part is the actual computational core, and the four parts on the side, on each side, are the high bandwidth memory. But these are then the drivers. If you're limited by memory bandwidth, your architecture is defined, not by the big bit of silicon in the middle, but these bits on the sides, which is what defines your memory bandwidth. So that's one aspect. Second is you have this fast memory of limited size. You're going to be limited by memory capacity again. So massive multithreading becomes essential, and careful memory management. And these things are not perhaps so common in big data today in the way we do analyze big data in commercial systems. But again, I think they will become more important soon. And the other thing, of course, is management of storage, and especially the I/O throughput from storage into this fast memory. So the problem here is that quite a lot of the conventional caching techniques won't work very well because the size of these high bandwidth memory stacks is around they're 60 gigabytes each or so, and the natural size of data we handle is similar size, so a few gigabytes. So there isn't, there's no space for a traditional caching mechanism where you have some sort of a learning thing which tries to guess, just brings in a lot of data and hopes for the best. You're not going to be able to do that. So what becomes very important are data prefetch. So actually understanding from the structure of your program which data will be needed next, and from the software side instructing the prefetch of the data into fast memory. So I think, and then those constraints drive the overall programming model, which looks something like this, and it's a mixture of lots of things, of course. So at the finest grain level, we have massively multi-threaded parallelism. We know we're going to need that. I think other people will too. Then we have a task-based, data flow-based parallelization, which is going to enable this data prefetch and dynamic load balancing, and also memory management. And then you have the high-level workflow parallelism, which is more simple-minded, more coarse-grained. And then finally, what we call observation-level parallelism, because obviously it's going to be multiple different observations looking in different parts of the sky. So I think the good thing is none of these things are new. I think everybody, we have technologies for this. You guys will all be familiar with some of those. I think we are placing some new demands on this and driving it in a new direction. But I think we in the Square Kilometre Array are confident we're going to be reuse many of the technologies that people are going to be talking in this conference today and tomorrow. So what the things we've tried so far, we've tried, and we are prototyping and evaluating many different technologies for many different parts of our system stack. We're looking at object stores. We are also looking at parallel file systems like cluster GPFS. We're also looking at network-attached block storage systems. In terms of low-level programming models, we're looking through the whole variety, from traditional Unix threads up to auto-tuning frameworks like Felido. And the higher-level programming models, again, we're looking at the whole variety of things. Yes, Apache Spark and other commercial-like big data products, but also university and research lab projects like Legion from Stanford or Swifty from Argonne National Lab. And we are looking at things like OpenStack and Slurm. So I think, how do I summarize what we found out? Well, I think we've broken all of those in some one way or another, of course. I think that's what we expected, because we're pushing it into a new part of the design space. Nothing works for us just out of the box. And the job we have at the moment is to decide really where to make our investment in order to make some of these technologies work for us in the way we need them to. So that is our current job. So if I just summarize quite quickly, so the Square Kilometre Array is the next generation international radio telescope and radio astronomy observatory. The reason it's been made possible are the advances in computing, and yes, Square Kilometre Array seeks to leverage those advances in computing, to create orders of magnitude leap in capabilities in radio astronomy. In terms of receptors and the way we capture the incoming light from space, it's all about mass manufacture. The key science drivers, like I mentioned, are gravitational waves and the very first stars and galaxies and quasars in the universe. The timeline for the Square Kilometre Array is that we're currently in the design phase, so we're expecting to complete the design next year. So we have maybe a year of work left to do, and then we begin constructions in 2018, The budgets are almost been agreed, and we're in the process of setting up a new international treaty organization, a little bit like CERN, which will actually handle the construction and the operation of the telescope. So the commissioning, we expect, will begin in 2020, and then full operations in 2023. So computing and big data, like I explained, are key parts of the design. We're relying on it. And it's going to be a key part of construction, and it's going to be an important part of operations as well. So I'll finish there. Thank you very much.